Okay, so we're going to talk about what I call the battle of the boiling points that makes things sound so much more interesting about intermolecular forces and their effect on different kind of properties of liquids. We're just picking on boiling point. We could have done any of the other ones because the same arguments are going to apply. Keep in mind that just about every single one of the situations here that I'm about to present to you are really going to be based on two different factors, or kind of two different ways of reasoning. One is that we are going to identify intermolecular forces, and we're going to keep in mind that not all intermolecular forces are created equal, right? That there are some that are just naturally stronger than other ones. Also, we're going to have to consider molar mass. So what you're going to typically be tasked with doing on, let's say, a fiesta of learning, is you might have to look at a list of molecules and then, based on their structure, determine which one has a higher or lower boiling point. Everything in this activity is going to be, we're going to identify the one that has the higher boiling point. And so what you pretty much do is, you go through, you identify all the intermolecular forces based on the structure, and then you take a look and see if there's anything, screaming at you about the molar mass, right? Typically, what you're going to see is you're going to have the same molar masses with different intermolecular forces, or the same intermolecular force with different molar masses, right? I'm not usually going to play the game where I switch two on you and ask you to judge it, but I guess you probably could after viewing a couple of these examples here. So make sure you grab that resource guide that should be posted somewhere on Canvas for this week's module, and we'll get after it. So this very first one, let's go through and we'll look at the two compounds that were competing against each other. The first thing that I notice is that I only have carbons and hydrogen. Even though that we haven't talked about organic chemistry yet, I will just straight up tell you that in this world that is based on carbons and hydrogens and different things like hanging off of those carbons and hydrogens, these things, just the hydrocarbon part is never going to be polar, right? It turns out that a carbon bonded to a hydrogen, and even though there's a little bit of a difference in the pull on those electrons, pretty much it's just no pull, right? And so there is no polar portion of either one of these. And so if that is something that is true at any point in the future where you say, well, it's nonpolar, well, that turns out that only London dispersion forces are going to be at all considered, right? And so both of these, and I'll just say, LDF for both of these in terms of intermolecular force. And so obviously nobody wins based on the intermolecular force argument, right? They both have, weak stuff going on, weak sauce, man. And so, well, what must be happening? Well, it turns out that London dispersion forces always depend on really the quantity of electrons that could kind of just at any particular point, maybe like there's a little excess in one spot than another. Turns out that you drastically increase that likelihood for something like this, right, where it's got a whole bunch more carbons, a whole bunch more hydrogens, right? And so in this particular case, even though London dispersion force is the same in both, this will win just based on the fact that there is more opportunity for London dispersion force. And so in terms of reasoning, you might say, well, this has a higher molar mass. Right? And then you could go in and explain the fact that, higher molar mass means more electrons, blah, 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 blah. So that's the first one. Let's take a look at a second one. The second one on the sheet looks like this. And so you do the same exact thing. You say, okay, is there any polar region of either one of these? Just a bunch of carbons and hydrogens bonded together. So both of these have London dispersion forces. Sorry if you can hear the dogs barking in the background, but I can't get them to stop. And so you say, okay, well, one of these must have a higher or lower molar mass. And then you look at them both, and they're both exactly the same, right? And you're like, well, you just said that most of these questions can boil down to two different factors. This turns out to be one of the rare ones where it actually has to do with what's called surface area, right? And so if you look back at when we talked about intermolecular forces, what we saw was that it is much more likely for something that is, really spread out over a big giant area. It's very likely that that thing is going to at some point, have some sort of imbalance of electrons relative to something like this, which is just kind of this big ball of stuff that doesn't really have as much surface area right here. And so I kind of think about it almost as if like these electrons are kind of like hidden and like we can't actually see them from the outside necessarily, right? And so it turns out that this one is going to have the higher boiling point because of its shape, right? And this is a really common kind of hydrocarbon / organic kind of question. Let's take a look at a couple more. Okay, our next competition is between methanol over here and dimethyl ether. You don't have to worry about the names of those things. So what are we going to do? Well, we're going to list off all the different forces that are possible. All right. Well, everything has London dispersion force, so you can just straight up write LDF as soon as you see anything. And then you go down and you kind of work through your list, and you're like, okay, well, what about a dipole? Well, it turns out, yes, oxygen pulls on carbon a lot stronger for that electron set. And by the way, if you need to look at an electronegativity list to ever figure out whether something's polar or not, you're absolutely welcome to do that. But I can say is that usually almost, we'll say 99.9% of the time, right, if you've got some sort of heteroatom like oxygen, nitrogen, fluorine attached to a carbon, this thing is going to end up being overall a polar molecule, right? And so that might give you a hint towards the fact that there are dipole-dipole interactions in this thing. And we kind of keep going up our list and we say, okay, is there any hydrogen bonding? It turns out, no, this one doesn't have hydrogen bonding because yes, it has hydrogens, but remember what we need is a NOF-H-NOF system, right? We need nitrogen, oxygen, or fluorine through space bonded to a bonded to a hydrogen that is itself bonded to a nitrogen, oxygen, or fluorine. So hopefully that makes some amount of sense because you watched that last video. So we're done with that one, right? We're going to go over here and we're going to say, well, duh. London dispersion force, dipole as well, right? And of course, like I should probably put the dipoles on here just so that, let's not use red, let's use blue, right? And so this guy has a net dipole that looks like that. This guy has a net dipole that looks like that. It turns out that hydrogen is even worse at pulling on electrons, so that oxygen is really pulling on those two electrons and making this end have a very minus charge, whereas this is a very partially positive charge. So we can say, go down our list and say, what about hydrogen bonding? Well, yes, in this case, right, there's my NOF-H, and then another oxygen, right? So another one of these, if it was bonded there, let's just draw it in so that I can show you what this looks like, right? We have this kind of through space hydrogen bond right there, right? And so this thing, in fact, has hydrogen bonding, and none of the other ones. And so as long as these guys are somewhere close in molar mass, right, that one absolutely 100% of the time is going to win the battle, right? So we'll put a nice big red check next to that. And you might be wondering, to calculate the molar mass of this, that's, 12 or 14 or whatever it is units bigger in mass than that one. But this intermolecular force thing really wags the dog, right? Eventually, you're going to get to the point, though, where, like, if this thing got big enough, right, it got bigger and bigger and bigger and bigger and bigger and bigger, eventually the amount of London dispersion force will kind of win. But I'm trying to make these more obvious, right, for you guys. I'm not trying to trick you. I'm just trying to teach you this, like, really useful subject. Our next pair is methanol versus sodium methoxide. Again, don't worry about the names. We'll go through and we'll list off the intermolecular forces. Luckily, this was in the last one. London dispersion force. Dipole-dipole. H bonding. And that's it. This one, as always, London dispersion force. Not really dipole-dipole, right? Well, I mean, I guess it's in an extreme sense it might be a dipole-dipole. Certainly not hydrogen bonding. But as you kind of work up your list there, you'll remember that that really, really, really strong intermolecular force was called electrostatic attraction. Right? And so that, remember, is the pull between, or the force between a full positive and a full negative, or multiple positives and multiple negatives. And that force is incredibly strong. And so it turns out that this one will have a much, 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 much higher boiling point than the other one. And just to be complete, right, we could also do molar mass and recognize that, oh wait, that one's molar mass is much higher. Doesn't really matter, because this really does, that's really the primary reason that the boiling point of this thing is so high. But you know, it's good to be consistent. So at least molar mass, right, that's higher, so everything is pointing towards that one. So hopefully this kind of gives you a little bit of help to do these kinds of questions. Obviously, if you were to explain it, you'd want to use a little bit better than my explanations here, where I'm just kind of doing shorthand. There's a whole bunch of other examples, wink, 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 on that resource guide that you may want to figure out, wink, wink, wink. I'll see you soon.